Right, welcome to Lecture 2, What Factors Affect the Rate of a Chemical Reaction. This is just a continuation of our unit on chemical kinetics. The essential questions that need to be addressed here in this lecture are what factors affect the rate of a chemical reaction, how do we use Maxwell-Boltzmann's distribution curves, and what do catalysts do? These are the questions that need to be addressed here and need to be answered so that you can take the quiz on this lecture. So first of all, let's review some important points from last lecture. Really quickly, remember that in order for a reaction to occur, reactant molecules must collide, but they must collide successfully with each other. And that means that they must collide with the correct geometrical orientation, and they must also collide with enough activation energy in order to overcome the activation barrier. In other words, they must have enough kinetic energy when they collide to overcome the activation barrier to stabilize the transition state. Well, there are two things that kind of relate to that idea that determine how fast a reaction will occur. First of all, the collisions must be frequent. The more frequent the collisions are, the faster the reaction. So that's important to think about. And then, of course, the kinetic energy. The more kinetic energy these reactant molecules have, the more likely they're going to collide, plus the more likely they're going to have enough energy to overcome that barrier. Now, these particular items that we have listed here, temperature, concentration, particle size, pressure, catalyst, all are looked at as ways to increase the rate of a chemical reaction or determine how fast a reaction occurs. And all of these points go back to either the frequency of collisions. The more collisions, the more frequent those collisions are, the faster the rate of the reaction, or deal with energy, the kinetic energy, in order to overcome that energy barrier of activation. And so those two things, frequency and kinetic energy, are important in looking at these factors. All right. So we're going to start out with looking at a Maxwell-Boltzmann distribution curve. We're going to draw several of these throughout the lecture. These are important that you're able to draw from memory, and so you'll need to know how to do this for the quiz and understand the interpretation of these curves. So let me start out by drawing the axes of these curves here. I'm going to draw it kind of big here. You might want to do the same on your paper because there's a lot here that we're going to look at. All right. So on the y-axis, we're going to put the number of particles. Okay? In other words, these are the number of reactant particles. So you might want to make note of that, the number of reactant particles. On the x-axis, we're going to have kinetic energy. Alright? And so what we're going to basically graph is the number of particles that have a particular amount of kinetic energy. And so a curve would look something very much like this. Alright? That's what our curve is going to look like. Now, what you're going to find is that the majority of the molecules have activation energies at the maximum height of this curve. So somewhere in here, let's just draw a line down here. This is the energy, this is the average molecule that has an average amount of kinetic energy. So we call this point here the average kinetic energy point. And then we have another special point right here, this area right there. That point here on our graph is known as the activation energy point. right? So molecules must achieve this energy amount of kinetic energy in order to overcome the activation barrier. All right. So this fraction of molecules that we see here underneath this curve, which is not a lot, only this portion of molecules has enough kinetic energy to initiate the chemical reaction. So there's not really, when you look at this, if you had 100 molecules, reactant molecules, only a very small percentage of those 100 molecules have enough energy to initiate this reaction, or in other words, have enough activation energy to overcome that barrier. So we could say that out of 100 molecules, 75% of them fit in this range over here, and they just don't have enough activation energy or enough kinetic energy to overcome that activation barrier. And so let's say only 25% of the molecules do. All right? So that's what this curve is trying to tell us, is really show us that only 25%, roughly, we'll say, has enough energy, kinetic energy, to overcome the activation barrier. The majority, 75% of them, don't have enough kinetic energy to initiate the chemical reaction. All right? And so what we're going to see is how these Maxwell-Boltzmann distribution curves are going to change when we change one of those factors, like temperature, concentration, adding a catalyst, and so forth, and how they affect this curve. And so we'll see that as we go along. Alright, so we're going to start out with temperature first of all. What we find with temperature, there are two major important things with temperature. First of all, that when we increase our temperature, we also increase the speed of these molecules, these reactant molecules. So if we increase their speed, we're going to obviously increase the frequency in which the molecules collide. So there's an increase in frequency of successful collisions. And again, as we said, the more frequent the collisions, the faster the rate of the reaction. Important for you to note. All right? But more important than that, more important than increasing the frequency of collisions, is that there will be an increase in number of collisions involving particles with the necessary activation or kinetic energy to overcome the activation barrier. All right? So what we're saying here is that when we add more energy to the reactant molecules, there will be a higher proportion or a higher percentage of molecules that now have enough kinetic energy to overcome the activation barrier. Got to think about this. This is very critical in your understanding about kinetics, is this point here. And what we have found is that for many reactions, to double the rate of the reaction, you do so by increasing the temperature by about 10 degrees. Increase 10 degree temperature, or the temperature by 10 degrees, you double the rate of the reaction, because there's a greater number of molecules that have enough energy to overcome that activation barrier. Right? Let's take a look at this with a Maxwell-Boltzmann's distribution curve. Really quickly, let's relabel our axis, or look at our axes here. So here's our y and x axes, and we're going to look at a curve in which our temperature, kind of low temperature. So we're going to look at a lower temperature here, like so. And then we're going to increase the temperature and make a curve for an increased temperature. Let me use a different color for that. And it's going to look something like this. Okay, like that. Alright, so this is going to be our high temperature, and our other curve is going to be low temperature. Okay, so write this down in your notes, so make sure it's there. Alright, now, where is our activation barrier? Well, it's still in the same place. Our activation barrier never changed. It's still there, or EA for the reaction. Okay, so initially we only had this fraction of molecules. Remember, only 25% had this original amount of energy, or only, we should say, only 25% of the original 100 molecules had enough energy to overcome that barrier. But notice what happened when we increased the temperature. It broadened out the curve more. And so we get a shift. Remember, this is the average that we started with. This is the average kinetic energy. And now, notice our new average has changed. This is our new average. The new average. So now more molecules have more energy, which should make sense. But what it also does is it increases the proportion or percentage of molecules that have enough energy to overcome that activation barrier. So now we have even more molecules added onto this. So we went from 25% to now maybe we're at 35%. Okay, so now we have 10%, or like 10% more molecules that have enough energy to initiate the reaction. And so as we increase the temperature, then we continue to broaden out this curve, and then more and more molecules have more energy that's larger than the activation energy needed to initiate the chemical reaction. And so, and this is what temperature does to the kinetics of a reaction. And so make sure you understand this Maxwell-Boltzmann's distribution curve very well. Alright? Okay, so now let's turn our attention to concentration. How does concentration affect the rate of a chemical reaction? Well, you can look at it very simple like this. You increase the concentration, so there's more molecules. Because there's more molecules, there's going to be more frequent collisions, more of them. The way I like to look at it is this as an analogy. You're in your classroom, and before the bell rings to dismiss from the classroom, if you go out into the hall, there's going to be less students in the halls. And so what is the probability that you're going to collide with another student in the halls before the bell rings? Well, the likelihood is not very great, okay? But if the bell rings and there's more students in those halls, what is the chances you're going to collide with another student? Well, it becomes much greater during the passing periods because there's a lot or higher concentration of students in the halls, and so there's going to be a higher frequency of collisions of students in the halls during passing periods. And so the same thing with reactant molecules. The more molecules there are, the higher the concentration, the more frequent those collisions will occur. And so if I was to draw kind of a diagram of that, what it would look like here, kind of a model here. If I had a molecule and it was moving, and another molecule and it was moving, and another molecule here, it's a very low concentration. There's not going to be high amounts of collisions. But if I take and I add more molecules, a lot more molecules here, now as they're moving, there's going to be more frequency or more likelihood that we're going to have collisions that are going to be occurring here. Right? So there's kind of a model diagram of this. Higher the concentration, more molecules, more collisions. The lower the concentration, the less frequent the collisions. The rate of the reaction is going to be slower. All right? So there's concentration for you. What about particle size? Particle size deals with surface area. And so what I want you to think about is if you have a big chunk, a large chunk of reactant molecule, crystal, right? And you take that solid crystal and you break it up into smaller pieces. Well, when you break it up into smaller pieces, you actually increase the surface area. So more reactants molecules are exposed to each other. So by increasing the surface area, by taking that larger chunk of crystal and breaking it up into smaller chunks, you increase the surface area. And so when you decrease the particle size, you're actually going to increase the rate of the reaction because there's going to be more opportunities for frequent collisions. Because the smaller particle sizes allow, or those smaller crystal sizes are going to allow more molecules to collide with more, or have more opportunities of collisions. So we increase the frequency. So what I want you to understand here is by increasing the surface area or by decreasing the size of the particles, those crystals that we're talking about, we will have an increase of the rate of a chemical reaction because there will be more frequency of collisions. Okay? So think about that. Okay? Pressure. How does pressure affect a rate of a chemical reaction? Well, pressure mainly deals with gases, so we're only looking at gases that are reactant molecules. Now, if you increase the pressure, the gas molecules will become more compressed. And that means the volume is going to get smaller, and so these molecules, these gas molecules, are going to be closer together. Again, if you increase the pressure, the gas molecules are going to become more compressed and get closer together. And so if they get closer together, they're going to be more likely to collide because they're closer together. It should make sense. And so there's going to be a greater frequency of collisions. So when we increase the pressure, the rate of the reaction is going to go up because there's more frequent collisions that occur. All right? Alright, so now the last thing we're going to look at is catalysts. Catalysts are very important in this whole idea. So what are catalysts? First of all, catalysts are going to be chemicals. Catalysts are not consumed during a chemical reaction. That's an important point to note. They're neither a reactant nor a product. Their only function is to increase the rate of a chemical reaction. That is their sole function. That is it. And so when we add a catalyst to a reaction, it should cause the reaction to go faster. Well, how does it do this? Well, it's simple. When a catalyst is added, it lowers the activation energy barrier. All right? It lowers the activation barrier. It doesn't cause more molecules to have, in other words, it's not like temperature where it gets more energy to these molecules. Instead, it literally lowers the activation barrier by providing an alternative route for the reaction to occur. So if we look at a graph table here with activation energy, so if you recall of our barrier here, right? So this right here is the activation barrier that needs to overcome. But if we add a catalyst, the catalyst literally lowers this barrier. So it actually changes the barrier, lowers it. So we don't need quite as much energy with the catalyst. actually makes the barrier smaller. Alright? So we're going to look at this idea with the Maxwell-Boltzmann's distribution curve. Let's see what happens when we look at this curve. So remember, the y-axis is the number of molecules and the x-axis is the kinetic energy. And so when I make the curve, like so, and we said that the activation barrier was right here, and this is the fraction or proportion of molecules that have enough kinetic energy to overcome that barrier, and we were saying that it was like 25%, okay, and then only 75% or 75% doesn't have enough energy to overcome that barrier. So what would happen if we add a catalyst? Well, the catalyst is literally going to change or move that barrier, right? So instead of the barrier being high, it's going to change it to maybe here. And so our new activation barrier with the catalyst is going to be here. Okay, so with the catalyst represented in green, and now notice there's going to be a greater fraction of molecules. And so now instead of 25% of the molecules that have enough energy, now it may be something like 40%. So it's gone up by 20% by just adding a catalyst. Alright? So catalysts are really important factors in speeding up a rate of the reaction, because it can have a dramatic impact on the number of molecules that have enough kinetic energy to overcome that activation barrier, as this graph indicates. Alright? So again, a catalyst, it is just a chemical, and all it does is lowers the activation barrier. In other words, the amount of energy needed to overcome that activation energy barrier to form a transition state by providing an alternative route. And so as you see from the Maxwell-Boltzmann's curve, is all it does is moves the activation energy state, which is represented in blue, to the one in green when we add a catalyst. Alright? So those are the factors that influence a chemical reaction. This is it for this lecture. Go back and review your notes. Excuse me. Make sure that you really understand these Maxwell-Boltzmann's curves, that you're able to draw a Maxwell-Boltzmann's curve for temperature and for catalysts and show the changes that occur there. Alright, and that is it for this lecture.